Whatever invasion. Yeah. Is that what they use right now? I mean, it's not, no, it's now old. Yeah, I don't use that stuff. Yeah, I don't use borrow it from. Yeah. Because it's only a problem in this room, right? That's where you have this from somewhere else. No, we can have a, for that, we can have also a better other for meetings. I think that. Okay, yeah, let's do that. But I mean, I can go. Yeah,
No, the website is down and that's fine. So
Okay.
I've sent the email. No, that's almost done. Mohammed, can you hear us?
Yes, Rakesh, very well.
Connect to the HDMI.
Yes, it's
That's the latest slides, right?
yes.
Okay, good. Is this working? Okay.
Yeah.
We're having technical issues. In the worst case, you can follow the slides on Zoom, right? If all of you have machines. Okay. Or phones are machines also.
There's only one. Oh, geez. No, it's not that.
No, I think
No, and it's problems.
we need to figure out what's the issue. Because it's a new hub.
Yeah.
Yeah. I think the hub makers are making faulty hubs so they can make more money, maybe. Just like RowHammer, right?
We don't have clicker now.
Yeah, it's okay. I don't need it. I mean, I want the clicker, but I think it's more important to get started now then. Okay. Was everything working? Online also? Microphone. So there are quite a few people online, I think. Well, chat. Okay, good. Somebody said yes, thank you. Okay, so let's get started. I'm going to remove this video panel and loading meeting controls. So before we get started, everybody has received their assignments, I assume, right? Everybody's happy? More or less. I think everybody got the top things that they asked for, so should be happy. Maybe you didn't get the slot that you wanted, but that's how it is. The early slots are, yeah, you have less time to prepare, and later slots have the advantage that you see what has happened, right? And you can synthesize better. But hopefully, I'm looking forward to a very nice semester with you guys presenting different papers. And I want to talk about RowHammer because the first set of papers are actually RowHammer. So this will be helpful for people who are going to present on the 30th of March. Does that sound good? Okay, feel free to ask questions. I have a lot to cover over here. And you've seen, if you've taken, how many people have taken digital design and computer architecture here? Okay, not everyone. But if you've taken it, you've seen me talk about RowHammer. But now you're going to see a lot more. And some of you are going to present the RowHammer papers. Who's presenting RowHammer related papers? Two? I think there are only two, so you're both here. You're presenting the Moisey Prime, or? Okay, you're presenting the revisiting RowHammer. That's great. You too? No, okay. I thought you raised your hand. Okay. So let's get started, I think. This is a fascinating story that still goes on, as you will see with the Moisey Prime paper and the revisiting RowHammer paper, actually. So basically, RowHammer is a reliability or robustness problem in general. And reliability can affect security, safety, privacy, all of those things in the end. And I like using this example. If you've taken the DCA, you've seen this example. This is a bridge. Well, are people in the back okay with that? Okay, that's a bit too bright for me, but maybe I'm too close. Basically, this is a bridge that is supposed to be robust and resilient, right? We rely on that. That's the word reliability. It comes from relying on something, right? We rely on this bridge being robust, but if you get a bit flip on this bridge, things like this may happen. And this is a real bridge that collapsed in 1940. It's in the Washington state of the United States. It's very close to where I used to live, actually, about 2 hours. And I did not cross this bridge because it doesn't exist anymore. It did this for, I don't know, 6 months or so, and then it collapsed. And the new version of the bridge has two bridges in place. So it's a double bridge. That's a good reliability principle also, dual modular redundancy, right? If one fails, hopefully the other one won't fail. Unless they have a common mode error, meaning you manufactured it in the same way such that they will fail in the same way. That's called the common mode error in dependable systems. And in general, it's very good to avoid components that have common mode error. At least don't use them for the same purpose at the same time, right? Okay, but that's the story of the galloping Gertie. And I think of RowHammer as bit flips happening in critical infrastructure like this. Another example, these people are constructing a city and they're sitting on a rod that's supposed to be robust, but if they get a bit flip, they will not be very happy soon after. Yes. The new bridges, I don't know. I didn't examine them. They look very similar, but again, common mode errors are a different thing. Yeah. You can look it up. That's your assignment now. Okay. But okay. So we're in general going to talk about robustness, but you can think of this as security also. These are clearly different concepts, right? reliability, safety, security. But reliability issues can affect all of them in the end. And I think of security as preventing unforeseen consequences. And going into the future, this is a mindset that's important to keep, in my opinion, because we'll be building systems, computing systems that we're going to use in all aspects of our lives. Like currently, people are all gung-ho about this ChatGPT-4 as if it's the most interesting thing in the world. I'm not convinced of that, frankly, but I see that there are a lot of security problems that it can open up, safety problems, reliability problems, and certainly misinformation problems that it can open up. So I think we'll need to have a good mindset of designing computing systems going into the future because we're going to rely on them much more so. So this is an example. I like using these pictures, of course, but you can think of it as a self-driving car. Would you trust your self-driving car to be able to sit on it like this without having, of course, additional controls that this Mr. Bean has in his self-driving car from 1990s? Okay. So yeah, basically bit flips will be problems over there. So RowHammer, I think a lot of you have seen it, but if you have not seen it, this is a phenomenon. And this is the phenomenon that enables one to predictably induce bit flips in commodity DRAM chips. Let's see. And when we first worked on the phenomenon, we found out that more than 80% of the DRAM chips that we tested were vulnerable. Basically, you could induce bit flips predictably. And interestingly, this is the first really documented example of how a simple hardware failure mechanism can create a widespread system security vulnerability. In the end, RowHammer is a hardware failure mechanism. And it's really a reliability problem. But it manifests itself as a security vulnerability because somebody can take advantage of it to take over the system, get some private data out of it. We will see different types of attacks basically. And as a result, people in popular media are writing articles that look like this. Forget software, now hackers are exploiting physics. And this is a good high-level description of RowHammer, in my opinion. But let me give you the story behind it a little bit, because this is something that certainly reliability is something we were interested in my group for some time. And this is an early paper. What's going on here? We really need to fix this problem because I think this was an issue earlier. Okay, I'll continue while you're trying to fix this problem. But we actually wrote this paper in 2013, as you can see, earlier than the RowHammer paper, where we argued that memory technology scaling is going to be a much bigger problem going into the future because memory is becoming much less reliable. And this is going to create all sorts of problems, performance problems, efficiency problems, as well as reliability, robustness, security problems. When we wrote this paper, we were actually working on RowHammer, but we didn't publish it at that point yet. So let me talk about this technology scaling problem a little bit. So DRAM, dynamic random access memory, is the memory technology that's used in all of our computers today. I'll wait for him to go quickly. But DRAM technology is a technology where you store charge in capacitor, and you encode the data based on the presence or absence of charge in a capacitor. That's 1 bit of data, essentially, capacitor. The capacitor must work correctly, and the sensing circuitry, access transistor, sense amplifier, and everything that basically enables you to read whether or not there's charge needs to work correctly or reliably, let's say. And if you were seeing that picture, basically it's a capacitor and an access transistor. And as you reduce the size of the cell, both of these properties become difficult to maintain. Basically, it becomes reliably operate the circuitry. Thanks, Akesh. And why do we want to reduce the size of it? So that we can store more data, more bits in a given area. That's the technology scaling base. That's what has enabled us to have systems that have large computational power by reducing the size of the transistors, and very large data storage by reducing the size of both the transistors as well as the capacitors. So there's a good reason to actually keep reducing the size of this. But unfortunately, if you keep reducing the size of this, everything here becomes less reliable and more vulnerable to noise. And there are a bunch of problems like this. I will discuss some of them. But basically, this scaling the feature size of DRAM was about 35 nanometers in 2013. And today we're around 10 nanometers. We're very close to 10 nanometers. This feature size basically depends on how DRAM manufacturers measure it, but the length of the transistor, let's say. So we reduced it. It's a measure of how technology scales.
But unfortunately, it has become very challenging because of these noise and reliability issues. But we want to keep reducing it basically. So there's a good reason why these things are happening. Okay, we've been actually doing some studies. This is a study that we did with Facebook for a couple of years while we were also doing RowHammer studies, and we published it in this paper, as you can see over there. But basically, we studied all of the memory areas that's present in the entire fleet of Facebook. And Facebook is clearly a huge company, and they have multiple data centers worldwide, tens of data centers actually worldwide. We had access to all of the memory area logs that they had in those data centers for many months, and you can see the number of months in the paper. And we basically looked at how do those errors correlate with system failures. And essentially, this is one example graph from that paper, which shows that chip density that's employed in DRAM in those servers have a strong correlation with the server failure rate we observe in the field. And again, server failure rate is a metric definition. You need to read the paper for exactly how it's done. You need to be very careful with these metrics, because if you actually don't have a good metric over there, you may not be able to see, you may actually see unexpected results, let's say. But this is the expected result, basically. If the chip density, the DRAM chip density that's employed in the server is larger, meaning cells are smaller and there are many, many more cells, you get more errors, essentially manifested in real applications in the field. So these are affecting real applications. And this makes sense because with smaller cells, with denser chips, you have smaller cells and more cells. So there's a lot more noise. Okay, so if you're interested, there's a paper. We're not going to cover it in the seminar. I'm not sure if I remember if we covered it in any seminar, but these are actually interesting studies in general. So of course, with this sort of studies, you cannot pinpoint what's going on. There may be different types of error mechanisms. So we actually built a lot of FPGA-based infrastructures. We're still using some of these. Unfortunately, I didn't update the slides with the latest versions, but you'll see some pictures later on. So this is basically the first infrastructure that we built. You have an FPGA that can test DRAM chips, and you can actually program the FPGA to do different kind of tests. For example, don't refresh the memory for 10 seconds and see what happens. Right? You can actually do very interesting tests. And then we built other infrastructures for the same purpose, for different purposes. And this is the RowHammer infrastructure where we did a lot of studies on. I'm going to talk about that. But this is actually open source. This is a version of it that was open sourced in 2017. We have a new version that's open source that works for DDR4 chips. But if you're interested in this, there's a lot of research that's going on with this sort of infrastructure. And you can learn a lot about existing memories with this. I believe we're going to have some papers on a random number generation using memory. Is that correct? Is someone going to describe that? No. In the past, in the seminar, we talked about, for example, how to generate true random numbers using DRAM. So this infrastructure enabled us to show that you could actually do that. You reduce the latency to access DRAM, and some cells fail randomly. And the fact that those cells fail randomly can be used as a random number generator. You figure out which cells fail randomly, and that's essentially a random number generation bit. So if you don't have this sort of infrastructure, it's very difficult to do those studies because you cannot change the latency to access memory if you don't have this sort of infrastructure where you can program the memory controller. Yes?
How do we know that the cells fail?
Yeah, there are tests that you need to do, basically. There are some tests that are defined to pass, let's say, through randomness. Yeah, it's always a good question, basically. You're as good as your tests over there that are defined. But there are some tests that are defined by NIST, for example, National Institute of Standards and Technology, and other countries have their own standards. Okay, so basically that's another study that you can do with this sort of infrastructure, and we're going to see some of those studies, I believe, in this course. I think somebody's going to present the PyDRAM paper. Is there anyone here? No? Maybe they're online and they're raising their hands, but I don't see them. Okay, so that's the reason we built this infrastructure, to understand the issues with memory. And you can read more about this if you're interested. So actually, the real reason why we built this infrastructure was to understand the data retention issues. So DRAM is dynamic random access memory. You need to refresh it so that the data stays, let's say, there. But as you reduce the size of a cell, the data stays less in the cell. So you need to refresh it more frequently as technology scales. And this is a problem with scaling. It affects performance, it affects energy. Clearly, right now, for example, my cell phone in my pocket is doing nothing but refreshing memory. It's in self-refresh mode. It's wasting a lot of energy, for example. If you did the calculations, if you took DDCA in a data center, for example, with petabytes and petabytes of memory, you're actually wasting kilowatt hours in power to refresh memory, just to keep the memory contents intact. And what we found out in some of these studies is basically there's a huge heterogeneity in the refresh requirements or retention time of these different DRAM cells that exist in a chip. It looks like this basically. Very small fraction of cells need to be refreshed very frequently, let's say every 64 milliseconds. A very overwhelming majority of the cells don't need to be refreshed at that rate, but you can relax the refresh rate to 256 milliseconds for that, for example. So this way, if you really understand what's going on here, you can reduce the refresh number of refreshes that you do by 75%. And that's a huge gain, clearly, right? You think about saving 75% of the power. And this also improves your performance. And these are old numbers, basically. Today, in some DRAM, I think 32 milliseconds is the refresh rate. And I think we're marching towards 16 milliseconds soon. In fact, under some conditions, it's 16 milliseconds, right? Every 16 milliseconds, you need to refresh DRAM at high temperatures. So at high temperatures, you actually need to refresh a lot more frequently. Okay, but of course, this is not that easy. So it turns out the retention time of a cell is dependent on the location of the cell, which this shows. It's also dependent on the value of the cell and the cells around it, because there's a lot of noise and cross-coupling that happens between the cells, and that affects the retention time. And it's also dependent on some quantum-like effects, like variable retention time. It's very interesting. We're not going to talk about it in this lecture, but a cell changes, a cell's retention time changes randomly during operation. We don't know exactly why it changes and when it changes, so it's not predictable, but it changes. So the question is, if it changes, if you test the cell at some point and you figure out that it has a retention time of, let's say, 32 milliseconds, can you trust it? It's not easy to trust, basically. That's one of the scaling problems, because this time dependency, this randomness actually increases as the cell becomes smaller and smaller. And we've shown this in some papers, not this paper, but this paper actually initiated. We wrote this paper that said, oh, you can actually shave a lot of refresh time as well as performance overhead. And then we said, actually, can we do it? So we built this infrastructure, and we said that, oh, maybe we cannot do it that easy. That's the paper that talked about a lot of these. And then we wrote a bunch of papers that talk about how can we do it actually? How can we get rid of refresh as much as possible without causing reliability problems? And I'm not going to go over these. So this, for example, deals with the variable retention time problem. This deals with the data dependency problem. And there are a bunch of papers that deal with a lot of different interesting things and propose a lot of interesting ideas. And you can see more recent chip actually have error correction capabilities, and they're also very, very interesting to understand. Because if you really want to get rid of refreshes, you really need to understand how the error correction that happens inside the chip behaves. Okay, but as I said, these are all works that were enabled by the infrastructure to understand retention time issues. But that was a major reason why we built this infrastructure. If you're interested, you can certainly watch more lectures on this. Okay, so while we were actually doing these studies, we were actually quite interested in other issues in memory. And one of the issues is read disturbance, which is what RowHammer is about. And we also had an infrastructure that's very similar to this that was built for flash memory. And we did a lot of studies on flash memory. I'm going to mention that later on. I don't have it right now. The picture, you will see it's again an FPGA-based infrastructure where you have a flash controller on FPGA, and you can change reprogram the flash controller so that you can test different things. And with that, we did a lot of read disturbance testing, and we were quite interested in whether that read disturbance also happens in DRAM. And we worked with Intel on this, and we found out basically that it does happen. And in fact, in predictable, you can actually do this in real DRAM chips out in the field. So that's what RowHammer is. So let's take a look at that. So basically, if you look at memory, it consists of rows of cells, multiple rows of cells. And in order to access a data value in one row, you can think of one row as, let's say, thousands of cells, thousands of bits stored. In order to access one of those rows, you need to activate that row first, meaning you need to apply high voltage to that word line so that you can read that row and then select whatever you read out of that row. This is called activation in DRAM. Now, if you want to access some other row, you pre-charge that row, meaning you apply low voltage to the word line, and there's some other circuitry that kicks in to prepare the array for the next access, essentially. This is called pre-charge. Now, if you keep doing this repeatedly, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, normally nothing should happen, right? But we see that you get bit flips in physically adjacent rows, meaning some cells in physically adjacent rows that are vulnerable to RowHammer flip. They lose their charge. And this clearly should not happen, as we said, right? Because you're not doing anything to those cells. You're not even writing to memory. So you should really not be changing anything in memory. So we call this the hammered row. We call these the victim rows. And we show that basically more than 80% of the modules that were manufactured by 3 major DRAM manufacturers are actually vulnerable to this problem. You can actually induce bit flips in more than 80% of them. I believe we could have induced more if we knew what we knew at this point. So that number might have been closer to 100%. But of course, I cannot verify it. I cannot go back in time and test the same modules at this point. Okay, but we know a lot more right now, basically. This is the first study that shows it. So, and this is a technology scaling problem because the chips that were manufactured in 2008, as you can see over here, that we tested, were not vulnerable to this effect. So the first appearance that we saw were from 2010, as you can see over here. And all of the chips that were manufactured between 2012 and 2013 had these bit flips. So why is this a technology scaling problem? Because as cells get smaller, they become more vulnerable to this noise. So what is this noise that we're talking about? Basically, cells are too close to each other. They're not electrically isolated from each other. As a result, when you access one row or one cell, you affect the value in nearby cells because of the electrical interference that happens between the cells and the wires that are used for accessing the cell. The wire is the word line, and the cells are on that word line, right? This is also called cell-to-cell coupling or interference. And I like this higher level abstraction. There are a lot of low level reasons that are interesting, which we're not going to go into here. I'm going to mention some papers that talk about some of those low level reasons. But at a higher level, if you apply high voltage or activate a row, an adjacent row gets slightly activated as well because you don't have perfect isolation. As a result, vulnerable cells in that slightly activated row lose a little bit of charge. And if you keep doing this repeatedly, those cells that keep losing charge, and at some point they lose enough charge that you cannot recover the value that was there anymore. Makes sense, right? Of course, there are actually much more detailed device level reasons that we're not going to talk about here. That's an interesting study also. So higher level implications are actually pretty bad because now these get exposed to the user directly, right? You have a bit flip in DRAM, and that DRAM is visible to the user, visible to the programmer, visible to the system, visible to anyone who can inspect memory in the end. And worse, someone can manipulate programs to actually, or write programs to induce these bit flips. That's what we're going to talk about, and this is what's next. So essentially, when we released the paper, we also released this open source code, which is very simple, as you can see. What this code does is it selects addresses X and Y such that hopefully they map to the same bank and same subarray, hopefully. And basically, this X and Y are activated repeatedly, right? So you need to avoid the cache hits from the CPU, of course, to be able to do that because this program is run on the CPU. So we flush X from the cache, and we avoid row hits to X by reading this Y in another row. So this is what the program does, basically. It activates X and Y in consecutive manner over and over. And if the chip is vulnerable, hopefully you'll get bit flips. Now, this is not the worst case access pattern to enable these errors because X and Y may be far away from each other, but we've also mentioned in the paper that if you actually sandwich only one row between X and Y, you can get many more errors. And later work actually took advantage of this. They called this double-sided hammering. So actually the results that we showed earlier was based on single-sided hammering. But if you do double-sided hammering where we sandwich one row, you get a lot more errors. And some chips could have been potentially vulnerable, even though they may not have looked like vulnerable to us at that point in time. So basically, if you run this program on an x86 system, you get errors, as you can see. And these are errors that we reported. This is early paper. Later works actually reported very, very similar things in the end. Okay. Any questions? Okay. So why is this a security problem? Because, yes. Yeah.
Why is the AMD have access to it?
That's a good question. I don't know. I don't remember. But basically, there might be something going on in the memory controller. And we didn't really reverse engineer it completely. Our goal was just to show that there are errors. But there might be something going on in the memory controller that's not enabling us to activate at a higher rate. Does that make sense? So in order to be able to get the error rate higher, you need to understand how the memory controller behaves also. They may be handling, for example, some of these instructions differently. They may be doing some reordering. So in the end, we don't exactly know the reason, but you get bit flips. And in modern other AMD systems, there are bit flips that are reported after this paper were much higher also. Okay, but that's a good question. It's always good to look at anomalies in the data. Yes. Yeah, that's a good question. I don't believe you get double, but you get a lot. Yeah, it's not a function basically. It's not a function of how many rows you're hammering in the end, but you get a lot more. So yeah, if you did double-sided, perhaps AMD would be much higher also, potentially. We don't know because we cannot repeat these experiments right now. We don't have the same system anymore. Okay, so basically this is a security problem because we're breaking memory isolation. And memory isolation is a very fundamental property, right? An access to one memory address should not have any effect on any other memory addresses, any unintended side effects. And this is needed for a reliable and secure computing system. And I believe we really need to maintain this going into the future. And we said that actually you can devise a program that can hijack your computer. Basically, we predicted that you could actually do security attacks, but we didn't have time to do that. And these good folks from Project Zero, Google Project Zero, who have discovered a lot of interesting, let's say, vulnerability issues over more than a decade, figured out how to do that. Basically, this is directly quoted from their blog post. They have a beautiful black hat presentation also. They don't have a paper on it, they have a blog post. That's the luxury of being in industry. They can write a blog post and everybody reads it, right? Especially if you're Google and if you're a security vulnerability person. But basically, this is quoted from them. They basically learned about the problem from our paper. They basically replicated the problem on their systems. They built 2 security exploits based on that. One of them takes over Google native client, which is not that interesting, but I'm going to get back to that later on. The other one takes over the x86-64 Linux. Basically, they have a nice attack, that's probabilistic attack, that can induce bit flips on an x86-64 Linux system using a user level process. And the basic idea is they do page table spraying. I'm not going to go over that, but basically they fill the memory with a lot of page tables to increase the possibility of bit flips. And they induce bit flips in page table entries. These are the page table entries that belong to the user level program that's hammering the memory. And they basically hammer memory and they use these bit flips to gain write access to the page table of that program that's hammering the memory. And now if you have write access to your page table, you can do anything to the system, right? Because you basically can enable yourself to have access to anything in the system. I like explaining this by saying that, for example, if you have a page table entry and if you actually want to gain write access to your own page table, you have a page table entry pointing to your own page table, and you have a write enable bit in that page table entry. If you flip that write enable bit from 0 to 1, you get write access to your own page table, right? So that's basically the conceptual view. Of course, this is very difficult to do because it's 1 bit out of the huge page table entry, right? That's why they have to develop a page spray attack to increase the probability of this attack. So actually, it's very interesting how they do the security attack. But again, we don't have time to go over it because there are many other security attacks that came after this. So this is called the DRAM RowHammer vulnerability, and I like this tweet from a famous hacker that says RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. Nice to have these analogies. So if you're stuck in this room, don't worry, you keep banging on the wall and hopefully one of the windows will magically open if the RowHammer is in effect here. Maybe, I don't know. So there are a lot of security exploits that people have looked at after this. For example, these folks from TU Graz showed that they could do these attacks in JavaScript and eventually they can gain unrestricted access to systems of website visitors remotely. These folks, actually, this is Kaveh Azavi's group. Kaveh is here right now. When he did this work, he was not here. But they basically showed that you could induce these bit flips deterministically in Android phones by taking advantage of the deterministic memory allocation patterns that happen in the Android operating system. Because basically, you can fool the operating system to allocate a page table entry to a location that you figured out to be vulnerable to RowHammer. because the operating system allocates pages in a way that you can reason about, let's say. And this is very interesting, actually. They had an app also. Similar folks showed that you could actually accelerate these attacks in a GPU because GPU has a lot of accesses that they can sustain to memory. You can actually do this attack across the network using the remote direct memory access interface that is present in modern data centers. And these folks showed the same thing. And these folks actually, they're actually interesting attacks. These previous attacks were taking over a system. But then later, okay, maybe you cannot take over a system easily because it's probabilistic. These folks show that even if you cannot take over a system, you can break confidentiality of the system. You can read some data that you're not supposed to read using these bit flips. And again, details of this are in the paper. And a lot of these papers were actually discussed in past incarnations of the seminar as well. This time we don't have it. And then there are these attacks where people showed that these RowHammer bit flips can reduce the accuracy of a neural network. There are multiple attacks. I'll show you a couple of them over here. This paper, for example, shows that if you do a RowHammer attack on a neural network, the accuracy may be initially good, but the attack leads to a neural network that has pretty bad accuracy because it changes the weights in a neural network in critical ways. So basically, it affects essentially all types of applications in the end. And then there are other things that I'm not going to talk about. It's another attack that you can do on your computer. I wouldn't recommend that. This could be a solution, but I would also recommend that. Okay, so I'm going to go into a little bit more detail, but if you're interested in detail, we've written a lot of surveys on this as well. This was an invited paper that we wrote that talks about a lot about RowHammer until 2019. And then more recently, we were invited to write this other paper that talks about more RowHammer, let's say. Any questions so far? Okay. So let's talk about understanding this element. I go into a little bit more detail because since we have this infrastructure, it's really important to understand it, because if you understand it, you can figure out how to prevent it also, or at least you know what you're dealing with. And unfortunately, understanding is we still need a lot more understanding. Let's say that's what we argue for in this paper, basically. Even though we have gone a long way understanding the problem, we still need to do more to understand it. And of course, we need to solve it some way, because this is not sustainable, right? You cannot have memories that you cannot rely on. Okay, so let's talk about understanding it. So this paper that we wrote initially about RowHammer did a lot of studies to understand it. And thanks to this infrastructure, we were able to do those studies. We tested more than 100 modules, as you can see over here. And there's a lot of results in the paper that I'm not going to go over. In the past, we've covered this paper actually in the seminar also. This year, we're not going to cover it. You're going to see actually a 2020 paper that I will briefly mention that did a lot more studies than this. So basically, let's take a look at what is the adjacency of the aggressor rows and the victim rows from the memory controller's perspective. So memory controller issues a row address. If the row address of the aggressor is X, where is the victim? Is it at X plus 1, X minus 1, X plus 2, X minus 2? That's the idea. From the memory controller's perspective, that's the really important thing over here. It turns out most of the victim rows are at address X plus 1 or X minus 1, kind of as expected, right? But there are some cases where those rows that are getting bit flips are at X minus 8, for example, right? Or X minus 7 over here, X plus 7. Yeah, they're not adjacent basically in the address space of the memory controller. So there are multiple reasons of this. Well, the main reason is basically internally DRAM does some remapping of the addresses. So what the memory controller sees as adjacent addresses logically may not be adjacent addresses physically. Okay. So later works actually did a lot of reverse engineering, and you can reverse engineer this mapping of what memory controller sees and the internal physical adjacency of the rows. So you can actually reverse engineer this. There's a lot of work that did reverse engineering. But from the memory controller's perspective, the bit flips happen in non-adjacent rows as well. So you need to take that into account when you're doing creating solutions. Okay, let's take a look at the access interval. One solution to the RowHammer problem is basically access memory less frequently. And then the question becomes, how much less frequently? Right? And this is the curve that you can get if you actually do these studies in the infrastructure. Right? These are the worst chips, worst A, worst B, worst C. These are from 3 major manufacturers. And less than 55 nanoseconds is not allowed across 2 activations to the same array. And if you actually increase that, you clearly see a trend in reduced errors, right? Errors reduce as you reduce the access frequency, activation frequency. And this is expected clearly, right? Because you're doing fewer activations. But unfortunately, you need to reduce the activation frequency a lot. You need to reduce the access frequency. That leads to fewer errors. And you can see that you go up to 500 nanoseconds. So this reduces the performance of memory a lot. So this is not a good solution off the bat. Does that make sense? You don't want to reduce the access rate and access of your memory. But we will see some solution that takes advantage of this observation to throttle accesses to particular rows that are identified to be hammered. You don't want to do this for all rows that you're accessing, because there are some cases where you access some row maybe 5 times, activate it 5 times, and then you're done with that row. But in some cases, you're accessing a row maybe 100 times, then maybe some alarm rings and you say, okay, this is not good. So I'm going to reduce the access rate to that row. Okay, refresh interval, this is actually important. Basically 64 milliseconds was the standard at that time. As you reduce the refresh interval, you'll get fewer bit flips. Why? Because you're reducing the amount of time as the cells can be activated, a row can be activated. And as a result, you're reducing the probability of a bit flip in the end. Yes?
When you hammer a row and then you, let's say, don't succeed in getting an error, then you take the break for row, then hammer the same row again. Is that the same as?
That's a great question. That's something you should really ask Song, because he's working on that. Anyway, not right now, but basically, hammering access pattern matters. If you take a break whenever you are accessing a row or activating a row, does it matter? And it does matter, yes. I'm going to mention a work that we did that talks about that briefly, but we have some other work coming up. So if you're interested, talk to Song. And there's a lot of research that can be done in that direction, actually. Okay, very good question. So basically, refresh interval is another thing. Basically, refresh interval determines how many activations you can do before the cells get refreshed, right? If you do more activations, meaning refresh interval is large, the probability of bit flip is high, as you can see over here in real system results. Right? So we showed that if you want to get rid of every single bit flip we've seen in these chips with our methodology, you need to increase the refresh rate by 7x. That's a lot, basically. So increasing the refresh rate is not a great solution, as you can see over here. And these are not the worst case attacks that you can do. We're doing single-side hammering. Double-sided will make that 7x worse, basically. Okay, so data pattern is another interesting thing. I've already animated it. But basically, if the data pattern looks like this in memory, you get fewer errors. If the data pattern looks like this, you get a lot more errors. This is because of the voltage coupling, again, between the cells, or capacitance coupling between the cells. And the coupling is higher if the cells are charged in different ways, usually opposite. Okay, and this data pattern needs to be discovered, of course. So data pattern matters, as you can see. And this is true for refresh retention time as well. Okay, so there are a bunch of other observations that we make in this paper. Victim cells, basically RowHammer vulnerable cells, are very different from retention weak cells. So if a cell gets, so if you reduce the refresh rate, a cell is vulnerable to errors, right? That's called retention vulnerability. These cells that are vulnerable to retention vulnerability are very different from cells that are vulnerable to RowHammer, because these are very different error mechanisms. It's important to see that. And again, if you're interested, you can talk to Song, because he has a lot of data related to it. Right, Song? Okay, good. Now he's doing a parallel processing. Okay, and then errors are repeatable, and this makes it a security problem, actually, because now you can figure out which cells are vulnerable and induce bit flips in those cells. So this could be because security problems happen if you can identify which cells are vulnerable and attack them. Right? And later works actually took advantage of this. You get as many as 4 errors per cache line. So simple error correcting codes that are used to detect and correct, let's say, 1 error, 1 bit is not enough. And this number has increased. These are studies from 2012 through 2014. Keep that in mind. Like the paper you're going to present is going to show a lot more errors. Okay, so cells are affected by 2 aggressors on either side. I said this, so this leads to double-side hammering, basically. There's a lot more results in this paper that I'm not going to talk about, but you can read it if you're interested. So RowHammer is getting much worse, and we're going to cover this paper. I'm going to mention this a little bit today also, but later we did this study because we wanted to understand what's happening to RowHammer. And one of the major reasons why we did this study was because manufacturers claim that RowHammer is sold. They're done. And we wanted to see whether that's correct or not. And I'm going to talk about that. And there are actually more RowHammer dimensions that need to be studied. One of them being what you mentioned, which is briefly studied in this work, but there's more to do in that area. And there are other things that need to be studied, like what's the effect of voltage, etc. Okay, now let's take a step aside and talk about solutions. Any questions on understanding? We're going to talk a lot more about understanding later on. And the paper, one of the papers that's going to be presented is going to be about understanding it. But let's talk about solutions. So solutions initially that were developed, first of all, there needs to be two kinds of solutions, right? There are some chips that are vulnerable in the field. How do you protect them? Unfortunately, there are very limited possibilities here because today's memory controllers are not programmable. You cannot program them easily. Basically, it's not like software. You send a software patch and you correct the error. Unfortunately, we cannot do that with the memory controller because the memory controller doesn't run any software that's patchable. It's really hard-coded hardware. There's very, very limited programmability by changing the refresh rate. And that's the solution that's going to be employed in the immediate term. But the longer term, of course, now you can actually change a lot of things, right? Potentially, DRAM chips can be changed, which is happening right now. Memory controllers can be changed, which is also happening. So both of them can be changed. So in our original work, we proposed both types of solutions. I'm not going to go over all of these solutions, but one of these solutions is proposed as the best solution. It's already employed. Variants of it is already employed in the field, but it's not good enough, as we will see. So one solution could be make better DRAM chips, like figure out some material that's different, such that we're not vulnerable to the problem. Unfortunately, we don't know how to do that, or even if we know, it's very costly to manufacture that material. Increase the spacing, make sure isolation is there. All of these actually impact cost. Some people propose, oh, why do we actually use DDR3? Use old chips with old technology. These are non-solutions, right? This is basically going backwards. Going backwards is not a solution, for example. Refreshing frequently, this is the solution that's employed in the field, as I will show you. But it's not a great solution because we want to get rid of these refreshes. As I said, right? We build this infrastructure to get rid of these refreshes. If you're at the cutting edge, you want to get rid of refreshes, not introduce more refreshes, right? That's the idea, basically. Let me put it that way. Sophisticated error correction codes, again, these are expensive in general in terms of cost, power, area, latency, etc. And also, there's a fundamental problem I have with error correcting codes in general. Is this the right solution for the problem? So the problem we're dealing with is a very particular problem that's access pattern related. It's not a random error. A random error, like error correction codes, were developed and put into memories to deal with random errors whose cause we don't know. A cosmic ray, this is the famous example. A cosmic ray strikes some machine and you get a bit flip. There's no other way of detecting this. Error correcting codes or duplicating memory. That's another way, basically. Error correcting codes are a smarter way of duplicating memory. It's you're doing some coding so that you don't have to duplicate memory completely. So in this particular case, I think fundamentally error correcting codes are the wrong approach. Because you know there's a specific problem and it's access pattern related, you can develop a much more efficient solution to it than protecting the entire memory with something that's really designed for random error correction. Okay, so that's important. Again, if you took DDCA, you know how I care about principled design. So whenever people propose error correcting codes, I get a bit wary at this. Now, error correcting codes can be employed in conjunction with some other methods. Now, that's a different issue. But directly using error correcting codes for this problem doesn't make a lot of sense in terms of efficiency to me. Okay, access counters. In our initial paper, we kind of dismissed this solution, saying that this is too costly, too complex. But I believe that this needs to be re-examined today, and people are re-examining it. Access counters means figure out which rows are accessed by how much or how many times, and try to do something about it. If for example, you have counters inside the memory or inside the memory controller, these counters tell you how many times each row is accessed. Of course, you can be smart about allocating these counters. You don't have to keep track of every single row. You can use Bloom filters, as we will see. And if you figure that out, refresh the adjacent rows to this row, for example, or throttle accesses to this row. Does that make sense? So you can basically reduce the impact of those rows. Okay, so what was employed in the field was increasing the refresh rate. This is Apple's security patch. Apple is nice because they actually accredited the real research that they worked from. And in the end, they increased the memory refresh rates, but they don't say by how much. Likely 2x, which is not enough to cover all of the bit flips that you can see as we have seen earlier, right, based on our testing. Because if they increase it by 7x or 8x, it's going to be a mess. It's going to be a lot of overhead. Okay, our solution, let me give you the key idea, was probabilistic adjacent row activation. And the idea is very simple. After the memory controller closes the row, it activates or refreshes one or both of the neighbors of the row with a low probability. And you can see the probability can be like this. And you can adjust this probability. It's a programmable value. And we showed that with a reasonable probability value that looks like this, you get error rate that's very, very low, let's say. And if you're not comfortable with that error rate, increase the probability. So there's a trade-off between error rates and performance overhead and power overhead. And this trade-off exists in flash memory, for example, in SSDs. That trade-off is already made. In DRAM, it's made, never told to anyone, but now we need to make it more explicitly. Okay, so basically the advantages of this sort of solution is it's low power, low performance overhead, as we showed. It's stateless. You don't need to keep track of any row. That was what really attracted us to the solution, basically. Don't keep track of anything, just do this probabilistically. And we showed that it's an effective and low overhead solution, given the state of the RowHammer at that time. But today, we're in a very different state. Technology did not scale very well, and this is actually a high overhead solution, as we will discuss. So this can be implemented in the DRAM chip, as well as the memory control, and both versions were implemented over time, actually. So how is it done in the DRAM chip? There's enough slack in the timing and refresh parameters, so you can sneak in some of these refreshes at some point. If implemented in the memory controller, it's a bit more difficult because memory controller needs to know which rows are physically adjacent to DRAM. And as I showed you earlier, we don't have this knowledge. So there needs to be some more coordination. And we always argued for that sort of coordination in our research. Basically, there should be more coordination between memory and the memory controller so that they can do things in a better way. Okay, hopefully that's happening going forward, but we'll see. So this was one Intel system that employed probabilistic adjacent row activation. So you can pick your, in the BIOS, it's not exactly how we envisioned it, but they had a BIOS level solution. Basically in the BIOS, you can pick your solution. You can say either 2x refresh. You can see that it's only 2x, and hardware RowHammer protection. And hardware RowHammer protection, you can pick your RowHammer activation probability that would induce these refreshes, additional refreshes. So this was a memory controller based solution. Unfortunately, Intel kind of stopped going through this direction because at some point, DRAM manufacturers said, we solved the problem. RowHammer is gone. You don't need to worry about it. And we're going to talk about that. Okay, so if you're interested, you can read this paper. Okay, so basically what we argued, and what PARA is an example of, probabilistic adjacent row example is an example of, is an intelligent control, slightly intelligent control that tries to deal with these errors. We're going to see a lot more intelligent controllers that were proposed soon. So for example, this was this flash-related studies that we did. This was our flash memory infrastructure that we used and did a lot of experiments on, including read disturbance. But if you look at flash memory, there's a lot of intelligence in the memory controller that's designed for flash memory. It can actually inspect a lot of things that's going on in the flash memory because it doesn't have the same unfortunate, let's say, interface that we're dealing with processor and memory. And if you're interested in what goes on in a memory controller that's designed for flash memory, there's a lot over here. Maybe I'll get back to this later on. Okay, I'm going to. So basically, let's say around 2020, DRAM manufacturers, as I said they solved the problem, and we wrote this paper saying that this needs more solutions and better solutions going into the future. Who was right? Any questions? So now I'm going to talk about what happened in 2022, but maybe it should be 2023. So I want to change it and mess up this setup. It was not that bad. Why does it automatically go into the presenter view? Okay, there must be some setting. Okay, so what happened, let's say, in 2020, 2023? I must also say that DRAM manufacturers were quite secretive about all of this, which is interesting because in 2023, they're writing papers about it. There's a paper from SK Hynix in the ISSCC conference. This is the first paper that was written by a major manufacturer that clearly uses the term RowHammer. And then there's another paper on archive from Samsung that uses exactly the same term, RowHammer. Finally, they're writing papers about it. But in 2019-20, it was not the case. Basically, they were saying we solved the problem. In fact, I gave an invited talk at a supercomputing conference. I talked about RowHammer in memory processing, and then a quite senior person from Micron. Micron is the third major DRAM manufacturer. Was the next speaker. He basically came up to the stage and said, we have a solution to RowHammer. It consists of 3 letters. Can you guess what those 3 letters are? ECC. Error correcting codes. But we know that it's not a solution, right? This was 2016, by the way. I'm not going to name that person. I think fundamentally he's good, but sometimes these people get into this company mindset that clearly messes up things. Okay. Okay, but basically, we wanted to re-examine RowHammer and figure out really what's going on. Are the DRAM manufacturers correct? Did they solve the problem? Or is this problem actually fundamentally easily solvable? Those were the 2 questions that we wanted to ask. And this first paper looks at the second question, basically. Is this problem fundamentally solvable? Where are we heading in RowHammer? If we get rid of all of the RowHammer solutions that are introduced, okay, assuming they work or they don't work, we don't care. Let's get rid of them. Let's disable them in the chips and let's test the chips. So you're going to present this paper, so I don't want to present it in detail. But basically, the takeaways from this work is that it's getting much worse. And the problem is not easily solvable, basically. We tested more than 1,500 chips, and we found out that newer DRAM chips are much more vulnerable to RowHammer. There are more bit flips that we see that are happening earlier. And there are new chips whose weakest cells fail after only 4,800 hammers. And basically, it's getting much worse. And existing mitigation mechanisms are not effective at future technology nodes. There's no mitigation mechanism that's described in literature that's good when your RowHammer threshold. When, for example, you hammer a row 1,000 times and you get a bit flip, there's no mechanism that actually works well. Either they don't work at that number, or they actually induce a huge overhead in terms of performance. So again, we built a bunch of infrastructures to test. You're going to maybe talk about those next week or 2 weeks later. Is it 2 weeks later? Yeah, 2 weeks later. And again, you can go over this more, but basically we did a huge scaling study of lots of chips, different standards, as you can see. And we found essentially the same thing across all of the chips. The problem is getting much worse. For example, this picture shows the RowHammer bit flip rate. This is the hammer count on the x-axis. This is RowHammer bit flip rate. And these are chips that belong to different generations. So you can see that going lower is worse. As we go from DDR4 chips to new DDR4 chips, the curve shifts to the left, meaning the first bit flip happens earlier with fewer hammers, and also to the curve shifts up high, meaning at a given hammer count, you get more bit flips. And that's true for across all manufacturers, as you can see. And this is a large scale study of chips. I mean, large scale from what we can do, right? It's 1,500 chips. It's not easy. To date, I believe this is one of the highest numbers, but maybe Hasan can correct me if he has more chips that he's testing for his new papers. I think the answer is no. Okay, basically it's difficult to test 1,500, that number of chips. Okay, basically technology is not on your side. So what's going on? Are the DRAM manufacturers correct? We'll see that. Okay, I'm going to skip these because I've said already these. And then the other study that we did in this paper was to evaluate the mitigation mechanisms. So basically these are different mitigation mechanisms and their performance impact, system performance impact. 100 is the best performance. If you go to 0%, you basically are not running your program anymore. For example, this is increasing the refresh rate. Increasing the refresh rate is not a good solution to get rid of all errors because your performance goes down to 20% of the level of what you would really want to be. You should really stay at 100% if you don't want to lose any performance dealing with RowHammer, right? And you can see that Para, our solution, we proposed Para, gets much worse after 1,000 or even earlier than 1,000, depending on how much performance loss you can tolerate, right? So only mechanism that scales is Para, but it gets very bad if the RowHammer bit flips happen after 100 hammers, for example. And then there's some other mechanisms that just don't work. And there's an ideal mechanism that's actually not bad, but there's significant opportunity basically in developing a solution, but we don't know what that solution is. This is in 2020 again. Okay, there are lectures on this also. So that's what this paper showed. And this paper, in conjunction with the next one that I'm going to describe, actually finally let the DRAM manufacturers get to their senses, because people read this paper and also the next paper. They basically said, we got to solve this problem. And the people who really initiated was not, unfortunately, the DRAM manufacturers. This was really the companies like Microsoft, Google, and Facebook telling the DRAM manufacturers, look what's going on. And these, that's the beauty of doing research in academia that can influence industry, in my opinion. In this case, that's exactly what happened. Okay, so this next paper is trespass. This basically here we wanted to as I said in this previous paper, we want to understand fundamentally what's going on with RowHammer, ignoring all the solutions. Here we wanted to understand DRAM manufacturers said, well, we solved the problem. Is that really true? Is the problem really solved? Can we actually induce these bit flips that are sold by DRAM manufacturers as RowHammer free? And the answer is basically yes, you can induce bit flips. So they did not solve the problem. They just claimed that they solved the problem. Okay, so this is the first work that showed that these protected DRAM chips are vulnerable to RowHammer in the field. So protections are called TRR. This is in the standard, in the DRAM standard, they added this TRR, target row refresh. It's a very nebulous concept. Just to give leeway to the manufacturers to implement whatever they want, in my opinion. But basically, it's a way of refreshing targeted rows due to RowHammer. DRAM manufacturers implemented some solutions, no question about that. But unfortunately, their mitigations were not secure. So in a sense, because they did not really advertise their solutions, publicize their solutions, they were really resorting to security by obscurity. So there are different ways of getting security, right? You can be fundamentally secure, provably secure, or you don't prove anything. You just say, we did something and live with it. That's what they did, basically. This is called security by obscurity. Somehow you obfuscate things or obscure things. But unfortunately, they couldn't obscure enough because you can actually find out things about these DRAM chips using infrastructure like ours, right? So this work introduced the memory-side RowHammer attack. So the idea is to hammer many rows to bypass these mitigations that are internal to the DRAM chips. For example, there could be a mitigation that detects some aggressor rows inside the DRAM chip. If you actually attack many rows, you can basically overflow those tables that are trying to detect those rows, and you're back to square one. Basically, you can induce these bit flips. I will show you a little bit more. This paper is not going to be presented this time, but in the past incarnations, we actually did this. And this also partially reverse engineered the mechanisms that are implemented in the DRAM chips and memory controllers. And we actually released an automatic tool that can effectively create these attacks. So you can actually play with this. Of course, there are newer tools. There's actually more research in this area, which is really moving fast. There are newer tools that build on trespass. Okay, let me give you an example. So this is a double-sided pattern. Red ones are aggressor rows, blue ones are victim rows. This is double-sided, but then you can have a third row that is an assist. So there are actually 3 rows hammering right now. Here you have a 4-sided hammer. You have 4 rows that are being hammered. And the sole purpose of this is to make sure that you bypass the mitigations that are internal. So let's take a look at that. So these are data from real chips. So for example, in this particular module, we get bit flips if we hammer 5 rows. We get bit flips if we hammer 13 rows, but there are no bit flips if we hammer 1, 2, 3, 4 rows. Right? It's interesting. So there's some noise. We don't completely understand everything, but there's some explanation in the paper, if you can see. In this particular chip, you need to hammer 9 rows to get bit flips. Okay. So the reason we were able to actually understand this is because of this infrastructure. If we did not have this FPGA-based infrastructure, this would be a nightmare to really induce. So based on experiments we did with our FPGA-based infrastructure by turning off the refresh, actually turns off some of these protection mechanisms. And by reading the paper, you can figure out what's going on. We discovered that there are 2 components to the in-DRAM target row protection mechanisms. One is a sampler, which tracks aggressor row activations. And this could be designed multiple ways. It could be frequency-based. Let's say it can record every nth row activation. It could be time-based. It can record n row activations. Or it could be randomly, similar to para. Regardless, the sampler has a limited size, and that's what we're going to exploit in the attack. Inhibitor takes action based on what's discovered by the sampler. It basically prevents bit flips by refreshing victim rows. And as I said, the latency of performing victim row refresh is squeezed into slack time available, as we discussed earlier, right? In the refresh command base. So if you understand this enough, you can actually develop an attack. And that's what we did. I'm not going to go into the details of it. You can read the paper again. But you can see that we found out that 13 of the 42 modules we tested, we can induce bit flips. And that's enough. That was enough for us. We declared victory because if DRAM manufacturers were correct, none of these modules we should be able to induce any bit flip, right? But we were able to induce bit flips in at least one module of all manufacturers. So you can see the best pattern is different for different manufacturers and different chips also. Okay, and we were able to show that you could actually do this on real mobile phones. You can actually take over the system. And you can read the paper for more details. And the attacks can be relatively quick. These are some attacks that were done in literature. For example, PT, page table entry attack, is very similar to the Google's attack. RSA 2048, this recovers the private key of the encryption procedure. And then there's a pseudo attack you can read again for those. But you can see that very quickly you can take over the system or achieve the goal you're trying to achieve with the attack that you're doing on real modules. Make sense? And we were not exhaustive, basically. That's what this last part is about. So basically, the key results of this work is that the mitigations that are advertised to be secure to protect against RowHammer are not really there. Well, they're there, but they're not secure. And mobile phones are vulnerable, DRM modules are vulnerable. And these results are actually scratching the surface. Our tool was not exhaustive, but it was very important that we publish this so that something really gets moving, let's say. So we could have, for example, waited to make sure we get bit flips in every chip. But what's the point in that? The extra engineering effort that's required for that is not worth, let's say, what we're trying to do over here. So it's always good to think about that. Is that when is that paper really ready? Would this paper be better written 1 year later with the extra engineering effort to actually show bit flips in every single DRAM chip that we tested? I don't think so. Then we would be 1 year away from industry really getting their act together and acting to solve the problem. Okay, but other people could use the Trespass tool and do more attacks, let's say. So basically what this work, and together with the revisiting RowHammer, showed that RowHammer is still an open problem, and security by obscurity is not a good solution. Okay, so there's detailed lectures also. Any questions? Yes, go ahead. That's a great question. I think, okay, there are two answers to this. Fundamentally, it has to be, no question about that, because DDR5 is a newer technology generation. As a result, unless the manufacturers are doing something like at the circuit level that's better, fundamentally, it should be vulnerable. Now, are there solutions that are employed that are going to be better than Trespass? I believe, hopefully, yes, because there is more flexibility in the DDR5 standard. There's something called RFM, refresh management. It's a messy command again, but that gives a little bit more flexibility to the memory controller to deal with things. But again, is that the final solution? It's not clear. It's not, basically, we don't know what exactly is implemented today. And nobody's claiming that it's not vulnerable. So they're not making this, the industry is not making the same mistake today. Yes, you had another question?
Are there actually any well-known incidents where specifically for RowHammer vulnerabilities have been leveraged by black attackers to launch back-to-full cyber attacks on critical?
Yeah, that's a good question. I don't know. I mean, no one has reported anything, but again, that doesn't mean that it may not have happened, right? We don't know. Yeah. With hardware security vulnerabilities, it's always like that, right? With Meltdown and Spectre, for example, which were a huge deal in 2018-19. Again, there's no documented case of something like that. Yes.
Overall, is there like a pattern of 0 to 1 or 1 to 0 being more common?
Yeah, so that's discussed in the papers. Yeah, I think one of the patterns is more common, but that depends on the encoding also. That depends on a bunch of things, how the values are encoded inside the chip, as well as how that gets expressed to the programmer. Yeah, so I think we reported in our paper, but also may have more data on that.
Yeah.
Yeah.
It's very complicated.
Yeah, exactly. There's a lot of things.
So there's like so first we have the true and anti-file thing. So it's like a cell can be encoded. Let's say a logical one can be encoded either as like
Charge or no charge. Yeah.
Yeah, charge or no charge. And second, we have let's say, assume a combined leakage path. Let's say the destination for this leakage path, like if it's the bitline or other sources, like the final leakage voltage will be different. That will also affect like which direction is more dominant. And finally, we have, let's say, yeah, just the data pattern will also affect like whether one kind is dominant compared to the other. And finally, we have like, whatever the process technology that the manufacturer is using, it might have a lot of different physics in there.
Exactly. So there are a lot of circuit and device level effects. And it's fine. You remember how many times you said finally. There's another more finally coming up that will affect things. So there are a lot of basically components to it. It's difficult to, yeah. But those are good questions, basically. Those are things that are being studied, and need to be studied more. Okay, so how to guarantee that a chip is RowHammer free? I'm not going to talk about this, but we did some work with Microsoft also on this one, and it's actually interesting. There's no, we wanted to understand from a, let's say, data center perspective, what are the access patterns that you can do in a program that lead to more bit flips? And there's some interesting results here, and there's no way to actually guarantee that your RowHammer chip that you're employing in your data centers, that the chip that you're deploying in your data center is RowHammer free. So later, we actually wanted to do more work to really understand what's going on inside the chip. So trespass work showed that solutions are poor, but how poor are they? Basically, can we develop a methodology to uncover the underlying protection mechanism in DRAM chips? And that's what this paper does. I will not go into it in a lot of detail, but this basically introduced a new methodology that leverages data retention failures to uncover how the TRR mechanisms internally really work, enable us to study their security. So we showed in this work that you can actually craft new RowHammer access patterns based on this understanding. You can almost completely reverse engineer what's happening inside the chip, inside the DRAM chip, to protect against RowHammer. And basically all of the modules that we tested are vulnerable. And you get a lot of bit flips, as you can see, and you get up to 7 RowHammer bit flips in one 8-bit data word. Essentially, ECC is ineffective in this case. And in order to protect for this using ECC, you need to have 7-bit correcting error, 7-bit error correcting codes, and that's expensive, as you can imagine. So okay, so we open sourced this also. So the key idea in this work is to use data retention failures as a side channel to detect when a row is refreshed by TRR. Basically, here we're combining our understanding of data retention behavior with our understanding of RowHammer. So we identify some rows that should not retain their data unless they're refreshed, and we turn off the refresh. If we turn off the refresh for those rows, and if somehow those rows retain data, that means that there's some internal mechanism that refreshes those rows. So now we have a side channel. So we can figure out the data retention time of all rows, and we can use this information to uncover when the TRR mechanism is kicking in. And with that information, with this sort of key idea, you can uncover almost everything inside a chip. And of course, we develop this infrastructure. So this enables us to get or construct new RowHammer access patterns that circumvent the TRR. And now you can see, actually, these are 3 major manufacturers, A, B, C. And you can see that they employ different aggressor detection mechanisms. Some of them use counters, some of them use random sampling, some of them, or some sort of sampling, not necessarily random. Some of them use a mix. Aggressor capacity, how many rows they're tracking is different, 16 over here, 1. Whether the tracker is per bank or not per bank is different. And when does the TRR or RowHammer protection mechanism kick in compared to the refreshes that are generated by the memory controller? What is the ratio of that? Again, you can see those are different. How many neighbors are refreshed? Some manufacturers, you can see, refresh 4 neighbors, just 2, as opposed to just 2 neighbors, because RowHammer effect actually is present. This is called a blast radius by industry. Basically, not only the immediately adjacent rows are affected, but other rows are also affected by RowHammer, to a lesser extent, of course. So these manufacturers are refreshing 4 rows, as you can see over here. And these are the rows that are vulnerable, maximum bit flips that we observe using our access patterns. And you can see the real HC first numbers for these. And these are relatively low, as you can see. HC first is when do you get the first RowHammer bit flips, after how many hammer counts? You can see it's 6K, 7K over here, double-sided. So basically, you can almost completely reverse engineer everything. This is the next step after the trespass work, if you will. Okay, I will not go into a lot of the detail, but essentially you can induce lots of RowHammer bit flips. And I believe actually, if you put a little bit more work over here, all of these numbers can increase, in my opinion. We didn't do a lot of work, for example, on manufacturer C. I believe you can reverse engineer, and their mechanisms are a little bit more complicated, actually, than manufacturers A and B. But if you actually put more effort, more reverse engineering effort, I believe you can actually find out more and craft better access patterns to circumvent. So this is what an attacker could do, basically. They can actually analyze these different modules, and they can actually craft attacks that are specialized for them. And ECC is not effective, as you can see over here. This is the bit flip counts. This is essentially, modules from all three vendors have 8-byte data chunks with 3 and more, up to 7 RowHammer bit flips. So conventional DRAM ECC, even strong DRAM ECC cannot protect against this easily today. Okay, there's a lot more in the paper, but we don't have time for it. So these are the kind of studies that I mentioned by fundamentally understanding. There's more to do to understand RowHammer. Yes. These are for the physical, yeah, because it's inside the DRAM itself, and DRAM manufacturers know exactly how they map internally the different rows. Okay, so let's talk about some new RowHammer characteristics, and this is something that is really important to examine going into the future. We need to understand this more, and we did the study for the Micro 2021 conference that talks about 3 major effects on RowHammer. One is temperature. The other is related to something you mentioned somewhat, aggressor row active time, how long you can keep the aggressor row active. And then the other is related to physical location of the DRAM cells. So we can go into more detail, but let me see. Okay, we still have time. And you can feel free to ask questions also. But basically, we enhanced our infrastructure for this purpose. You can see that this infrastructure is more precise right now. The temperature control is within 0.1 degrees Celsius. That's important. And we did a lot of tests. Here we were not able to test a lot of chips, partially because these tests are extremely long tests. But you can see that we actually tested 4 major manufacturers, but the 4th one is very small actually. The DRAM market is dominated by the first 3. They're not necessarily ordered in terms of how big they are. Samsung is the biggest, SK Hynix is second, and Micron is the third. Okay, so basically this paper looks at different things, as I said. And there are 3 major findings. One is a RowHammer bit flip is more likely to occur in a bounded range of temperature that's specific to a cell. So unfortunately, this calls for more understanding. Basically, we don't quite fully understand the relationship between temperature and vulnerability to RowHammer because it seems to be very, very cell-specific. But it happens to be happen at a bounded range of temperature, and the bounded range is different for different cells, essentially. So there needs to be more here. Second, if the aggressor row is kept active longer, this leads to more bit flips, and there's more to do in this area. And some certain physical regions of DRAM are a lot more vulnerable than other physical regions. So all of these can be used by the attacker or the defender. Attacker can use this to craft more effective attacks, and the defender or protector, let's say, can use this to design more effective and efficient defenses. Let's take a look at this relatively quickly. So for example, this is an X-axis pattern where you're activating aggressor rows as frequently as possible. Row A is active, row B is active, row A is active. You're doing double-side hammering. Here, we're activating row A for some time, keeping it open for a while, and then waiting. After that, we're activating row B. It turns out if you do this, this leads to more bit flips for circuit level reasons that we briefly mentioned in the paper. So this is a better access pattern for an attacker. So attacker can actually induce bit flips earlier. And this is bad for the defender because if the defender assumed or put in a defense, assuming this sort of aggressor activation pattern, then bit flips will happen a lot earlier than expected, and the defense may not be able to catch that. Right? So that's why it's really important to really understand what's going on. And there's more here. And if you're really interested in this, talk to Hassan. Okay, spatial variation. As I said, RowHammer vulnerability significantly varies across rows as well as columns because of manufacturing-induced variation. You can read the paper for more detail, but this is a pictorial demonstration. On the y-axis, you see the HC first, hammer count, minimum activation count to observe a bit flip. On the x-axis, you have DRAM rows sorted by reducing HC first. And you can see that there's a huge variation, right? Across DRAM rows, there's a big variation. Across DRAM modules, there's a big variation also. So these are different manufacturers. They all see a huge variation. Some rows are very vulnerable over here. Some rows are not so vulnerable over here. Okay, there's more data on this, and you can see more details. Again, I'm going to skip this because I gave you the major observation. That's true for rows. That's true for columns also. Some columns are a lot more vulnerable than other columns. And again, the reasons for this, we don't fully understand. Part of the reason is basically manufacturing variation, right? Different wires and different cells have different vulnerability because of manufacturing variation. Maybe there's no, and as far as we can see, there's no exact pattern to these. But if you can somehow figure this out, you can make your defenses a lot more efficient. Basically, today's defenses are assuming the worst case. So every row, what does that mean? Every row is as vulnerable as the worst possible row that would get bit flips. Worst possible row gets bit flips with 1,000 activations, for example. If you assume that your defense needs to cater for every row with the same protection capability. But if most of the rows are not that vulnerable, and that's what we see basically, 90% of the rows are half as vulnerable with this metric, HC first metric, then you can reduce the aggressiveness of the solutions. This leads to significant area reduction in tracking aggressor rows. So these are two mechanisms. I'm going to discuss one of them that basically track aggressor rows and refresh victim rows or throttle aggressor rows to protect against RowHammer. Their tracking mechanism can be made much more efficient. So this is an interesting direction also. And then there's the temperature, but I'm not going to talk about that. There's interesting observations here. Okay, so this work basically goes deeper into RowHammer, as you can see, and uncovers some things that we didn't know about. Any questions? And whatever you uncover, it's always good to think it could be used by the attacker and it could be used by the defender. It's always that dual. And if you're interested, you can watch Giri's video. So let's talk about more RowHammer analysis. Very briefly, we also wanted to understand the effect of word line voltage on RowHammer. So we updated our testing infrastructure such that we can, in a fine-grained manner, change the word line voltage. So you can see the power of this sort of infrastructure right now. This is the infrastructure that doesn't exist anywhere else in the world, let's say, except we open source it, of course, so people can build it if they want to. But this sort of infrastructure enables us to understand things at the cutting edge. So this work basically shows that if you reduce the word line voltage, this is reducing the activation voltage. So this is reducing, intuitively, this should reduce the impact of RowHammer bit flips, right? And that's what we see basically. This reduces RowHammer vulnerability. Unfortunately, it also adds some not so nice effects, like it increases the activation latency because voltage is lower. It also reduces data retention time. And we discussed this in the paper. I believe you can get to a better situation by considering all of these. But I don't believe this is the final solution. So reducing the word line voltage, we wanted to understand the effect, and we did achieve that understanding, but I don't think you can actually do a lot with the reducing word line voltage. And that's also really important to understand, in my opinion. Okay, so you can watch another talk of Giri. Now let's talk about solutions. So I'm going to talk about RowHammer solution. This is something we developed, and this was a finalist in Intel's Hardware Security Academic Award contest last year, or maybe this year, well, for 2021, let's say. But before I go into it, let me talk about these solution approaches. So this is another slide that talks about solution approaches more broadly. So the first one I'm going to dismiss. The second one I'm going to dismiss because there's good data that shows that these are very difficult to do today. The third one I'm going to dismiss for different reasons. So people have proposed physical isolation. Why don't we isolate aggressor rows from victim rows? Just put some buffer rows between them, right? Now, this wastes a lot of memory, clearly a lot of inefficiency. This also is not perfectly secure, as other works showed. And then the question becomes, how many isolation rows do you need? How do you decide that? So this actually has a lot of hairy issues. And then there are two major solutions that I believe are interesting, which is reactive refresh. Figure out which rows are rapidly activated in some way, count accesses to them, for example, or do probabilistic adjacent row activation. It doesn't count them, but it probabilistically figures that out. And then refresh the adjacent rows, right? So this has some problem because if you implement the memory controller, you need to know the mappings. And then there's this other solution which has not been examined to great detail, which is proactive throttling. Figure out which rows are activated a lot, throttle accesses to them. Instead of refreshing the victim rows, throttle access to these rows. Now this is good because this doesn't require you to know which rows are adjacent. So this could be easily implemented in the memory controller. That's why proactive throttling is nice. So all of these actual solutions are interesting because they all have a trade-off between cost, power, performance, and complexity. So the perfect solution to RowHammer is not known yet. All of the solutions are a trade-off. Of course, there's security also. Which ones are fundamentally secure? You need to prove the security of your solution as well. So this is what we wanted to target with the RowHammer work. I kind of gave you the idea, but we wanted to make sure the solution is scalable as RowHammer vulnerability becomes worse into the future. And we wanted to make sure the solution is compatible with commodity DRAM chips. We don't want to know which rows are physically adjacent. We don't want any information from the DRAM chip, and we want to be able to implement this in a memory controller, let's say, without information from the DRAM chip. So that's the idea, and without modification to DRAM interface also. So the key idea is selectively throttle memory accesses that may cause RowHammer bit flips. At the high level, we use area efficient Bloom filters to detect which rows are being hammered a lot. And you selectively throttle accesses from within the memory control, stop accesses to those rows basically for some time. Of course, to be secure, you need to make sure you detect every row that may cause bit flips, and also you throttle it long enough such that you don't get bit flips. And the paper discusses that. I'm not going to go into exactly how this works, but bit flips do not occur in the end. There's a security proof. And optionally, if you do this, you have an advantage because now you know which rows may be hammered, and you can inform the software. And I think this is really important going into the future. If there's some RowHammer type of attack that may be happening, informing the software could be useful, right? Okay, I already said this. There's no need for proprietary information or modification to the DRAM chip with this sort of solution. So there are two components to this. One is row blocker that tracks row activation rates through area efficient Bloom filters, and blacklists rows that are activated at a high rate, and throttles activations targeting a blacklisted row, all in the memory controller. No row can be activated at a high enough rate to induce bit flips. Okay. Attack throttler is some other component. This identifies threads that perform a RowHammer attack. It reduces the memory bandwidth usage for those threads, such that non-attacking threads can use memory better. And this is really important. And this is one distinction of RowHammer compared to other solutions. This greatly reduces the performance degradation and the energy waste that a RowHammer attack inflicts on the system. And based on this, you can optionally report it to the operating system. Okay, so we did a lot of evaluation of many state-of-the-art mechanisms of many different metrics like system throughput, job turnaround time, unfairness across different applications, DRAM energy consumption. And turns out RowHammer's performance energy overheads remain negligible, less than 1% in this case. And also, this is when no RowHammer attack is present. When RowHammer attack is present, RowHammer actually is better than other solutions because it reduces the impact of the attack on the system. It reduces by providing less memory bandwidth to an attacking thread. So you get more performance and less energy consumption. So this sounds good, right? And if you're interested, the paper has a lot of actually analysis of different types of protection against RowHammer. Again, I'm not going to talk about that, but since we don't have time. Okay, this is also open source, and you can actually build on it. If people are interested in solving RowHammer, there's a lot of actually open source material that we have, and there's a lot of expertise in the group from multiple people. So if you're excited about doing something like this, definitely talk to us. Because this does not completely solve the problem. Why? You may say, basically the hardware cost is still high. Even though the hardware cost is more scalable compared to other mechanisms, unfortunately, it's still pretty high. And it's a bit less complex than other mechanisms. So competing mechanisms, for example, graphene is a very competing mechanism. It uses a frequent item detection algorithm, Mies-Ragri's algorithm that's proposed in the literature, adapted to hardware. It's nice conceptually, etc. It has a security proof just like RowHammer has, but it's very complicated to design in hardware actually. But it's a good solution, I think. The major problem with these solutions is the hardware cost and the complexity right now. So there's a lot more room, in my opinion, to solve RowHammer. Okay, but you can also look at the open source code because we released RowHammer open source along with 6 state-of-the-art mechanisms. Okay, so this is an example of another intelligent control. This is what I was really referring to with intelligent control. Now we have an intelligent control that's keeping track of which rows are being activated a lot and doing something about it. Much more intelligent than Para. And Para is more intelligent than existing memory controllers. Okay, let's take a look at these solution approaches again. So we need to, I think, solve RowHammer in better ways. What else can we do? So people have proposed actually row migration-based RowHammer dependencies. That's not included in these solution approaches because there's not enough space in the slide. Somehow we need to reconstruct the slide. But basically, these are migrating rows. This is an interesting approach. And the idea is to dynamically remap an aggressor row address to a different physical row before a RowHammer bit flip occurs. It doesn't require refreshing the victim rows, and it reallocates the aggressor row's data. So the way it was proposed in this work is you go through the memory controller. I don't think it's a very efficient approach. I don't like going through the memory controller unless it's needed. But there are a bunch of these defenses. Okay. I think these are not the latest version of the slides, I think. But fine. At least 2023 is correct. Or maybe I couldn't send you the latest version of the slides for some reason. Okay, so there are a bunch of these that are being proposed right now. Yeah, migration of rows is a bit tricky in my opinion, because once you start migrating rows, you actually cause a lot of data movement. That's another thing we want to get rid of, right? You don't want to be migrating rows all around the memory system a lot. So it's good to think about these principles, in my opinion. While this is good to explore the solution direction, I'm a bit skeptical that this is going to be really the solution to RowHammer. It may be part of a solution when no other solution works, let's say. But having this as the only solution to RowHammer is a bit difficult to really digest, because you're causing a lot of data movement in the system, right? Especially when your RowHammer threshold is low. Imagine a system where after 100 activations, you get a bit. Now, even benign applications today are doing that almost. Some applications access rows, activate a row 100 times within a refresh interval. So now you have a benign application, right? You may be running multiple applications that are actually getting close to that limit, or maybe exceeding that limit. They're not attackers, they're benign applications that you and I are running without any purpose of attack. Okay, so there's more RowHammer in 2020 and 2023. I'm going to just show you what has happened. So there are a lot of papers that are being written. As you can see, there are sessions actually. And this is the premier conference, IEEE Security and Privacy. There's a RowHammer session, as you can see. Major security conferences, major operating system venues actually talk about RowHammer also. I didn't include everything over here, actually. There was some more that I missed. There are attack papers, there are defense papers. You can see that there are papers. This is last year's IEEE Security and Privacy, ASPLOS, HPCA, so even a reliability physics symposium. So it's very interesting, I think, what people are doing. So this is a paper that was written by Google. I like this one because they basically showed that you can actually increase the bit flips by enabling another row. So by assisting hammering from a row that's a bit far away. That's the idea. So this basically takes into consideration the distance from the row. It doesn't immediately hammer adjacent rows. Well, not a lot, but hammers some other row that's a little bit farther away. And this helps as an assist. And they show that basically by doing this, you can some existing defenses can lead to attacks, because existing defenses refresh adjacent rows. And if you're actually using those refreshes as activations that hammer that row, but helping that hammering with some other row that's a bit far away, these existing defenses that refresh adjacent rows can actually lead to attacks themselves. So that's the interesting part in this paper, in my opinion. So if you read this, it's very interesting. Yeah. So there are more works that I'm not going to talk about, but it's very interesting. So we've been doing works also. This is Guy's work. And we've been actually writing papers that talk about more transparency in the memory system. Let me talk about this solution relatively quickly. So this is an idea that's actually more general. We call it the self-managing DRAM chips. The basic idea is to enable autonomous operations in DRAM. So one of the reasons these solutions are difficult to implement and adopt in practice is DRAM doesn't have a lot of autonomy, right? Memory controller dictates everything that the DRAM does. The DRAM manufacturer is kind of in a bind, basically. They cannot do something that they know is good, even though they want to do it, because the current interface between the processor and memory is not flexible. Processor dictates everything, or memory controller dictates everything. Whenever the refresh is done, whenever RowHammer defense gets activated, etc. So we basically argue that there needs to be more autonomy for DRAM. And the key idea to enable this is to prevent the memory controller from accessing DRAM regions that are under maintenance. DRAM now has the capability to reject some commands, some activation commands. Memory controller says, activate this row. DRAM says, sorry, I cannot activate it. I'm under maintenance in this particular location. And you can bound this time, of course, right? So that's the idea. You can add another pin to the DRAM chip for this. That's the cost. And leveraging this ability to reject an activation, a maintenance operation can be implemented completely within a DRAM chip. And this maintenance operation, what is the maintenance operation? Refresh is a maintenance operation. Fundamentally, DRAM chips should be doing it without the memory controller being involved. Why should the memory controller be involved in this, right? DRAM chips, if the DRAM manufacturer knows exactly how to do this efficiently, it should be done transparently to the system. But today you cannot do it because the interface requires the memory controller to be the master, let's say, and the DRAM cannot be autonomous. RowHammer protection could be another example of this. And memory scrubbing the memory to see which errors have happened and correcting those is another thing. So again, I don't want to go into all of these, but this self-managing DRAM enables efficient implementation of all of these. It also eases the development in DRAM such that bigger steps can be taken, because some of these changes are difficult to realize because you need to change the interface such that the memory controller can do it. And once you try to change the interface between the memory controller and DRAM, a lot of politics comes into play. Because in industry, the way you make these changes happen is there's a standards body called JEDEC, Joint Electron Devices, blah, blah, Corporation, something. But basically, they dictate the interface. There are hundreds of companies that are part of it. And all of these hundreds of companies somehow need to agree with some majority voting or, I don't know, plurality voting to make a change. And getting those companies to agree on one thing is not easy, even if that thing is simple. Now imagine complicated changes like interface changes that are big, it's very difficult basically. But if you give some freedom to the, or breathing room to DRAM, then it actually enables a lot of progress and innovation without requiring those changes, essentially. That was our idea. But of course, with any good idea, you get a lot of rejection. This paper gets rejected, let's say 4 or 5 times. But we don't give up on the idea, let's say. Okay, we may talk about rejection later on. So if you're doing research and getting rejected, don't worry, you're not alone. Many Nobel Prize winners have gotten rejected multiple times. Yeah, including Einstein, actually. I have a favorite story about Einstein. So Einstein sent a paper to a journal saying that, could you publish my paper? And this journal editor sent him a couple of reviews saying, look, we reviewed your paper and do these changes. Einstein said, I didn't send you my paper to get comments on it. I just said publish it. So there are a lot of interesting things, I think, that are kind of reducing innovation in the way publications are handled today in systems. So, but Einstein's point is very well taken from my perspective, because he knows what he's doing and he wants to publish it, let's say, right? Yeah, today reviewers actually reject ideas for almost no reason. For example, the RowHammer paper that we discussed that was published in 2014 could have been published in 2013, but it got rejected from the conference that we sent it to, saying that this is not a real problem. That was the comment. I can show you the comments, but if you have time later. But keep in mind that there is some process that goes on in every paper that you read, that you're going to read, and that you're going to see in this. And sometimes I may tell stories like this. Today we don't have sometimes stories for the RowHammer paper. Maybe later I'll discuss it. But good ideas get rejected. They don't necessarily get accepted right away, let's say. And it's not necessarily for good reasons. Usually, sometimes it's for very unfair reasons. For example, with the RowHammer paper, the comment we got was, this is not a real problem. The reason they thought this was not a real problem is because we did not show it in real applications. For them, this access pattern was not real, meaning a security, like this sort of attack is not real for them. So this is calling security is not real, in other words, right? So that doesn't sound like a very fair comment. Okay, okay. So there's more going on in RowHammer, as you can see in IEEE security and privacy. There are more works. They're actually very interesting papers. Some of these papers we covered. This cryptographic security and integrity against RowHammer, we covered it in last semester's seminar course. Okay, so there's more to come. Now let me conclude. Any questions, by the way? No questions? Everything is good? Let me talk about some future elements. So future is getting much worse, basically. DRAM is becoming less reliable, more vulnerable. More issues may be appearing. RowHammer is becoming bigger, perhaps. There could be other types of errors. And these errors could pose security vulnerabilities. And this is not just true for DRAM, it's true for flash memory and emerging technologies. But DRAM is very special today because its main memory is directly exposed to the programming language and the system, right? Flash memory is a little bit farther away, right? There's a huge storage stack that you need to go through. So it's a bit harder to really launch security attacks due to flash. Reliability issues, yes, no question. And then there are emerging technologies that are proposed to replace DRAM, but they all have their own problems. So this is from our paper from flash memory. You can see that there are many, many error types On the Y over here, program erase cycling, programming errors, cell-to-cell interference, data retention, read disturbance, as you can see. And there are a bunch of mitigation mechanisms over here. If you're interested, you can, again, read this paper that I mentioned. And we need to build intelligent controllers for security, safety, reliability, and scale. And I believe actually intelligent controllers can enable this. That's what we're working towards right now. But more methodically at a high level, we really need methods for, I think this is a 3-step methodology for understanding these issues and solving these issues. We need to really understand what's going on. That's why all of these studies that I mentioned are really important. How do we understand? What are we dealing with? Can we model it? Can we predict it? And we really need real device data and analysis for this, and reliable metrics to really conclude some things out of it. And that's what we've done in the RowHammer research implicitly. I've described a lot of it. And then the solutions need to be architected in a principled manner, in my opinion. There should be good partitioning of duties across the stack. You cannot give up performance and efficiency. There could be multiple solutions employed together, in my opinion. I don't think there's a single solution to RowHammer at this point. In my opinion, it needs to be multiple solutions employed together. But performance and efficiency are important. And I think going forward, patchability in the field is important also, because who knows what else are we going to see with technology scaling. And design and test are very important, in my opinion, because we need to design, automate the testing, and do online testing while the system is in the field. So one of the issues that are out in the open is what happens to RowHammer as the system ages, for example. You have a system that's out for 10 years. Is this still good? You have a system that's out in space. Is that still good? Right. What about these things, basically? I think that's why online testing and patchability are really important. So there are 2 major future RowHammer directions. One is understanding. As I say, aging is over there. There are many effects that still need to be rigorously examined. I will leave it at that. And solving. More flexible and efficient RowHammer solutions are necessary. And I believe co-architecting system and memory is still important, because there's this divide between system and memory that's not very good for overall system design today. Okay, that's what this paper argues for. If you're interested, this paper has essentially surveys the work and basically argues for these two major things. Okay, so we argue for that in other papers also. And this self-managing DRAM that I mentioned is really a way of better coordinating DRAM and controllers such that each of them can do what they're good at. Today, memory cannot do what it's good at because it doesn't have the freedom. Now let's give it the freedom such that it can do what it's good at. And memory controller can deal with what it's good at and what it's really supposed to be doing. Okay, understanding and modeling is done with the infrastructures, as you can see. So we're getting close to the end. Any questions? Yes, please.
Actually, many of the building and designing new vendor architectures to avoid or prevent attack. But what about system other and reliable solutions?
You mean existing architectures that are out in the field?
Yeah.
I mean, as you can see, DRAM manufacturers put some solutions. Are they reliable enough or secure enough? That's a good question, right? That's why we're doing these studies. I think if you really want to make something completely bulletproof, it's very difficult to do, I think, with the existing solutions that are employed in the field. That bar is very high, I think, today. You will need to, let's say, refresh like 10x more, 16x more. So you have to basically take a huge performance and efficiency cut. I think basically you can do it, but it will come at a big, very large cost. You see what I mean?
Yeah.
So bulletproof security, bulletproof reliability it comes at a huge expense, unfortunately, because of the way the solutions are implemented. They're not perfect today. Yeah, but our goal is perfection, because if you see these errors like once in a million, then they should be happening every day, right? Because of the law of large numbers, right? Okay, that's a very good question. So let me go to bridges over here. This was my favorite bridge, but we have a lot of these bridge incidents. This is Seoul, Korea. This is Minneapolis. This is Genoa. And more recently, this is close to another place that I used to live in. This is in Pittsburgh. There have some beautiful pictures, as you can see. It's not that beautiful if you're one of those people inside those things. Now, the good news is there was no fatality in this one. I cannot say that for the other ones. But basically, we've been building bridges forever, and clearly we have not figured it out how to do it bulletproof yet. Right? That's an example. Some of these are actually due to aging issues. This one in Pittsburgh is actually due to aging issues and lack of maintenance, etc. But even though we've been building bridges for thousands of years, we didn't get it right. I don't think we're going to get memory right. But the good thing is, with memory, we have this patchability. We have this controller or software that can actually protect against it. We just need to design the system such that it can patch it. Right? With bridges, unfortunately, you cannot patch those things. Or you can patch them at extreme costs, perhaps. Right? So it's good to think about this. So this goes back to basically what we have argued for more than a decade now. We really need to be taking a systems architecture perspective for this. So I should also mention that industry is writing papers about making memory controls intelligent. This was a paper that was written by Samsung and Intel. They did not mention RowHammer in this. This was 2014. It was very sensitive. But they did mention some other DRAM process scaling issues, and they said we should really be co-architecting memory and controllers. This is the only paper that they wrote together that I know of. These companies, they don't normally talk to each other unless there's an army of lawyers on either end. And then if you have an army of lawyers, in the end, you're not talking to each other. Or even if you have one lawyer, let's say you're not talking to each other, let's say you're doing something else, let's say. Okay, so let me give you final thoughts. I know we're a bit over time. You can go if you want, but there's actually something even more interesting here. So this is a slide from Satya. Satya is a distributed systems expert at CMU. He was my former colleague. He actually, when I told him about RowHammer, he was very excited. He immediately incorporated into his course, distributed system course, as an example of Byzantine failures. Basically, Byzantine failures are characterized by undetected erroneous computation. It's opposite of fail fast. Basically, if you have a failure, the best system is quickly fail with an error saying I cannot proceed anymore, or give no result. Whereas RowHammer violates that, right? You get a bit flip and you don't know about it. And erroneous can be malicious. Intent is the only distinction, basically. It's very difficult to detect and confine these Byzantine failures. Do all you can to avoid them. This is, again, his slide. And again, Lamport defined this Byzantine general problem. That's why it's called Byzantine failures. I don't have time to go over it, but you can read this beautiful paper. So before RowHammer, there was actually some understanding of memory errors. This is a beautiful paper from 2003, as you can see. And this was also presented in the seminar in past incarnations. These folks said that, oh, we can induce memory errors in real machines, and we can actually take over the Java virtual machine. And they did it. The way they induced errors was with this lamp. So they took this lamp, it's a heat source, they put it next to memory, and a bunch of bits flipped. And probabilistically, they were able to take over the Java virtual machine. They were able to get out of the sandbox as a user level program. So this is a beautiful paper. It's actually very interesting. I read it a lot before I started doing research on RowHammer. But in a sense, not a lot of people took this seriously, right? Because if you think about the security community, who's going to launch this attack? You have to have physical access to the machine. And it's a very, very probabilistic attack because you get lots of errors in the system. You're lucky basically if your system doesn't collapse because of that. So basically, RowHammer is replacing that lamp with a much more precise mechanism in software. You can think of it that way. That lamp is gone, no physical access needed. In software, you can induce this error. As a result, a lot of people got interested, basically. That's why you see this action in the security community, because they saw real chips are vulnerable in a simple and widespread manner, and this caused real security problems. And this reliability security connection is now mainstream. Even though we knew about this connection, there's no question about that, right? As that paper showed, now it's mainstream, right? Because you could actually do this in real chips. So that's why you see a lot of RowHammer attacks. I believe there's more to come. Let's see if we see in DDR5, as you asked the question. Of course, the bar is higher, right? To attack real systems right now, because defenders have raised the bar also. So it's going to be more and more difficult to launch these attacks, but it may be possible still. And there are many new RowHammer solutions that are being proposed right now. Initially, people were not taking this so seriously, but I think right now there's a lot of seriousness, and there's a lot more solution papers that are being presented in both security and architecture venues. I believe there's more to come over here. And as I said, finally, the industry is actually publicly writing papers about it. Industry meaning major DRAM manufacturers. Okay, I think there are also other repercussions, like RowHammer enabled a shift of mindset in mainstream security researchers. Now people are thinking general purpose hardware has a lot of issues. RowHammer is one example that started, but what else is there, right? If you're a security researcher, that's actually great thinking, in my opinion, great mindset. What else can I discover? And people who worked on RowHammer actually started working on other stuff in hardware. And two of the groups that discovered Meltdown and Spectre, these are actually microarchitectural side channel attacks, heavily worked on RowHammer attacks before. So now there's a lot of literature on hardware security, actually. If you go to these conferences, architecture, security, operating system, there's a lot of research on hardware security in general. So there's more to come. And we're going to see some more hardware security papers that are going to be presented in this seminar also. Okay, so let me conclude with the slide. Memory reliability is reducing. Reliability issues open up security vulnerabilities. And once these are open, they're very hard to defend against. RowHammer is a prime example of this. And I already said this. I think implications of RowHammer on system security research are tremendous and exciting, and they're still there. The bad news is RowHammer is getting worse. The good news is we know a lot about it, and we have a lot more to do. But I think we have a better mindset right now than where we were 3 years ago, right? 3 years ago, industry was saying, oh, we solved the problem, forget about it. Now, they're not saying that. Even when they write about solutions, they don't talk about RowHammer solved. This is a solution that reduces the vulnerability. Okay. So we're now fully aware hardware is easily fallible. We're developing both attacks and solutions, and hopefully we're developing more principled models, methodologies, and solutions. And if you're interested beyond the papers that we're going to cover, one of them is going to cover the Revisiting RowHammer paper, and the other is going to cover coherence-induced RowHammer attacks, which is also quite interesting. So one of them is an analysis paper, and the other is a defense paper. No, attack paper. They have a defense also, actually, in that paper. So it's going to be interesting. And these papers actually give you an overview. This is a short paper that gives you the state of the art very quickly. Let me put it that way. It's only 8 pages later. Okay, I think I'm going to stop here. Otherwise, I could keep going forever. Any further questions? Okay, then I'll see you next week. And then after that, we're going to start with your lectures, let's say. And we're going to talk about how what we're going to do in those lectures, because we're going to introduce a couple of new things this time. Yes? You should contact your mentors. Yeah, if they did not contact you, definitely contact them right away. Yeah.
Supposed to meet online or?
I mean, that's up to you. However you prefer. I think mentors are available both online or offline, depending on your choice. I would suggest in person. That's always good, but again, that's up to you guys. Yeah, basically, if your mentors are assigned, please contact them as soon as possible, especially for those of you who are presenting in 2 weeks. But don't wait, even if you're not presenting in 2 weeks. Any other questions? Yes.
Are we only going to have lectures or presentations on the days that are published on the website where some where participants are going to do presentation? Because I think not all Thursdays or scheduled.
Yeah, the not scheduled Thursdays are, I think, holidays. I believe. I don't think we have skipped because we have enough people. I think we have 19 presentations total. Yeah. Unless you want to come here during a holiday and do a presentation, probably not a good idea. Okay, so we're not going to have lectures basically on the non-scheduled days. Okay, then we're done. I'll see you next week. Take care.